wires do really weird things when they're near each other. So let's take it one thing at a time. So actually I'm going to color code this. So let's have our blue wire here. We will name this blue wire, give it a name. Joseph. Joseph, the amazing current carrying wire. Okay, so the wire, we're going to make this wire have a current going up. We are now going to learn in another right-hand rule. Hopefully you've read the notes. We're going to learn another right-hand rule. I'm going to go through it with you really quick. All right, so back to our wire Joseph. Okay, as we said, doing our right-hand rule. Oh. Over here, Joseph's magnetic field points into the page. It will be stronger closer to the wire, so I really should draw it like this, but I'm kind of rushing here. Okay, and over on this side, it's going to be coming out of the page. Okay, so now let's put another wire near Joseph, who we will call Stan. Okay, which way do you want Stan's current to be flowing? Up or down?
Down.
Okay, let's do down. Okay. All right, so here's Stan. All right, now notice Stan is now a current moving through a magnetic field. What happens to particles moving in a magnetic field? They feel a force. Very good. Okay, so we got to find the direction on that force. Well, what do we use to do the direction? Yeah, our right-hand rule. So Stan is going down. So you're going to take your thumb, which is your first set up your fingers. Take your thumb and point it downward, okay? Now, rotate your hand, twist your wrist around, keeping the thumb pointing downward so that the magnetic field finger, which is your index finger, points up out of the page, okay?
Oh, I always think like out because I'm looking.
If you look, your F finger should be pointing to the left. Should look a little bit like this, where this is your I. This is pointing straight up, but it's hard with this camera. This is your B, and this guy was your F, okay?
I see your F.
So that means that Stan is going to feel a force pushing him this way. Newton's third law, for every force, there is an equal and opposite force. What does that mean for Joseph? Which way is Joseph going to be pushed? The other way, right? So that's why in that MIT video I gave you, they flew apart, okay? So you could tell which direction the currents were going. Joe just asked a really good question. Joe, you're not a YouTube star. Say hello. He has signaled hello with his eyes. He's ready for fame. Okay, so Joe went... oh, thank you, Joe. Very well done. Okay, so Joe just started a problem. I asked them really quickly, like, what would happen if they were going the same way? So Joe started out, and he did something that I think is very good, very diligent. Okay, I should draw this better. He drew both wires, and he drew the magnetic field for both of them, okay? So he started out by doing this. And he drew this guy's as well. And he asked a very good question. He asked, what's going on in between them? Okay, well, I'm going to talk about that with you in a second. But let's pause. The reason Joe got confused, which is he was just being very diligent, is he drew the magnetic field of both. I don't think that's a good way to start this problem. I would actually just draw the magnetic field of one, put the other wire into it, and then just look at how the green wire would be affected by the blue wire first. Don't think about anything else beyond that right now, okay? We'll address your question in a second. So if you just focus on making one magnetic field, putting one wire in it and figure out how that second wire is going to be affected by that magnetic field. Don't draw the magnetic field of the second guy. You will get confused. Okay, hey guys, so I'm recording. We're going to answer Joe's question, though, because it's a great question. He's like, all right, what happens if you have two wires? And Joe kind of hinted at the answer. Okay, I'm just gonna draw. I'm not gonna draw this very well because I'm kind of rushing here to get us some time. Okay, so that's one, guys. Now this guy over here, he's got his own magnetic field. Oh gosh, I really drew that terribly. I'm sorry, I'm rushing here. This is where people really will hate me on YouTube. This is why Brendan keeps marking down my videos. Okay, so look in the middle there. Okay, in between them, you have one guy's magnetic field pushing down into the page, the other guy pushing up. What is going to happen dead in the middle of these wires if they have the same amount of current and they're the same distance from them? They're going to cancel out. Very good. So in the middle there is kind of like a no man's land of no magnetic field. In fact, if to Tony's question, if you laid a little wire perfectly down in the middle there, nothing, because there is no magnetic field there. Okay, so mu naught times the current times 2 pi r. So let's just talk about that. This is the current, obviously. Mu naught is a constant. You can look it up, put it in your calculator. 2 pi, obviously a constant. And r is, if you imagine kind of like an invisible circle around here, r would be how far away from the wire you are. Okay, so the further you get away from the wire, the faster your magnetic field is going to drop off. Okay, so this is B and this is R. Okay, so if you wanted to calculate the force on one wire acting on another, that can get pretty interesting. That's actually a kind of interesting little math problem. So here we have two wires, Erica and Jess, named after my best friends in high school, still my best friends. Okay, so let's find out how Jess, or let's do Erica would affect Jess. Let's switch flip them this time. So if we wanted to know how much magnetic field, just focus on what Erica's doing first and then how Jess is affected. So if we wanted to calculate how much magnetic field Erica is causing on Jess, well, first of all, it's going into the page. Again, I'm not drawing this well, sorry. It's actually stronger close to the wire, sorry. And we say that they're a distance of d apart. Okay, the equation there would be the magnetic field from Erica is equal to mu naught times the current in Erica divided by 2 pi, and we said r was a distance of d apart. Okay, that's how strong that magnetic field is. Now, if we want to know how much Jess is affected by that, the equation is F is equal to, so this is where it gets interesting. Erica caused this magnetic field. That is the magnetic field that's going to affect Jess. Jess has her own separate current, okay? She has her own length here. Okay, so she's got her own length and she's got her own current. What would the sign of theta be? What would be the angle between the magnetic field and the current? What is that? Just looking at the picture.
Wait, between the what?
Between the current, which is going down, and the magnetic field, which is going into the page. 90 degrees. What's the sign of 90 degrees? 1. So this equation is basically F is equal to I, L, B, and the sign of theta was 1, so we don't even have to think about it. So the force on Jess would be Jess's current, the length of Jess, and the magnetic field came from Erica, so it would be mu naught I over 2 pi d. That would be the force Jess would feel. Fun question they love to ask. if that's the force that Jess would feel, and I think they're going opposite directions, so they would be apart, right? Am I crazy? Let me do math.
Is
Burp.
that eye in
Burp.
there, eye of Erica, the blue one?
Huh?
Is that eye, the blue eye, is that eye of Erica?
Yeah.
Yes. Wait, I think they come together. Hold on, I gotta do this in my head real quick here.
Good question.
Okay, hang on. Down. Okay, the B is into the field. Okay, so yeah, apart. Okay. So, if this is what Jess feels that way and she feels this amount, how much would Erica feel the other way? The same, because of what law? Newton's third law. If they ever give you, like, this force is called this, what is the force the opposite way? Every single time. Newton's third law, same amount. Take it as a freebie, and they love to ask questions like that. Okay?